the subject of this lecture is actually different than what is written in the schedule. It is convergence to equilibrium under variable curvature bounds, while the title originally was Poincaré Inequalities and whatever I said earlier. So Max, please go ahead.
Thanks, Boaz. So I apologize in that Boaz is right. The title in the schedule is more appropriate, and that I will spend more time talking about Poincaré inequalities than convergence to equilibrium. Yeah, so this is based on a joint work with Patrick Cattiot here in Toulouse, as well as Arnaud Guillan in Clermont-Ferrand. And roughly speaking, for those of you who are already familiar with this, is the goal was to go beyond the Bacry-Emery criterion for convergence to equilibrium and Poincaré inequalities for diffusion processes, using an average notion of curvature rather than pointwise lower bounds. So to talk about the setting, it's really going to be about long-time behavior for the following stochastic process. So we take a gradient descent equation and we add a Brownian noise to it. So here we have some potential V. We seek to minimize it, but we still have some kind of noise. So this is a Markov process. It has a nice explicit generator, which is the Laplacian distorted by a first order term that takes the gradient of the potential. So this is the generator acting on functions. And for normalization procedures, I will assume that V grows to infinity fast enough so that exponential of minus V is integrable. And up to adding a constant, we assume that this total mass is 1. And then it turns out that there is a unique invariant probability measure for this diffusion, which is the measure with density exponential of minus V. And the question we were looking to is how fast does the law of xt converge to this unique equilibrium measure? And there are numerous motivations from this. One is about that this kind of equations arise for several models of statistical physics. For example, the n-particle system Jalil Shafai spoke about in his talk yesterday can be written in this form. But it is also useful for a question that arises for numerical simulations. Say we want to simulate this measure mu. Well, one way to simulate this is to design a Markov process that has mu as the invariant measure. So this is one possible Markov process that has the right invariant measure. And so one way of simulating mu is to simulate this dynamic and wait for a long enough time so that we are close enough to the invariant measure. And of course, to have theoretical guarantees on how efficient this kind of simulation is, we need to know how long it takes for this dynamic to go to equilibrium. Okay, so here a bit of so once we start thinking about how fast we converge to equilibrium, we need to talk about what notion we use to measure a rate of convergence. And of course, there are many ways of measuring the rate of convergence, and one is to look at what happens is to look at L2 convergence. So here, if we look at the generator of this diffusion, this is a symmetric operator in the L2 space weighted by mu. And therefore, long-time behavior of the process will be related to the spectrum of the generator. So if we integrate by parts, we can see that the integral of the operator L applied to some test function f multiplied by g is just the average of gradient of f dot product gradient of g. So this here includes the symmetry of L. And then it says that having a lower bound on the positive eigenvalues of L is the same as looking at a Poincaré inequality. and controlling the variance of some test function by some constant times the L2 norm of the gradient. And in which case, the inverse of this constant Cp is a lower bound on the positive eigenvalues of minus L. So why are we looking at the variance and not the L2 norm? Of course, it's because if we apply this generator to constants, we get 0. So the generator has a kernel, it's the set of constants, and we're looking at what happens orthogonally to the set of constants. So functions with average 0, and then their L2 norm is the variance. Okay, so it's the same thing as looking at bounds on eigenvalues is the same thing as looking for good constants in these Poincaré inequalities here. And indeed, we can show that as soon as a Poincaré inequality holds, if we start with some, if we look at the density of the law at time t with respect to mu, then the L2 norm of the density will decay exponentially fast, and the rate of decay is controlled by the Poincaré constant. Okay. So here, since the topic of the conference is concentration of measure, I guess I should talk a bit about the connection between these Poincaré inequalities and concentration of measure. And it turns out that these Poincaré inequalities actually imply sub-exponential concentration properties. If you look at any, if you have a Poincaré inequality, and then you look at deviation from average for Lipschitz test functions, they decay exponentially. And we can control the decay rates by the square root of the Poincaré constant. So in here, the constants are, I don't think this is the version with the sharp constants, but okay, the sharp constant in the exponential decay property should be in general comparable to the square root of the Poincaré constant. So in general, the implication is in only one direction. Poincaré inequality is stronger than sub-exponential concentration, but the reverse is also true if we have if V is assumed to be convex. So this is a result Emmanuel proved a bit over 10 years ago.
Thank you, Max.
Yeah. Sorry, Boaz, I didn't hear you.
It could be my problem, but I keep for 15 seconds, I could not hear your voice. Maybe other people did hear your voice, and it was just my connection.
Okay.
Since I have a hard time hearing you,
I think it's just your connection.
It's probably your connection.
Yeah, I have a hard time hearing you, Boaz, too. So is there anyone else with who has a hard time hearing me, or?
I can hear you very well. So.
Okay, then sorry, Boaz. Okay, so another important property of these Poincaré inequalities, which kind of govern, which are one of the motivation why we're interested in, is the tensorization property. If you look at an n-fold product measure, the sharp Poincaré constant is also the Poincaré constant of the marginal. So this tensorization property is at the root of the fact that these Poincaré inequalities tend to behave quite well in high dimension. Okay, so there are, of course, many tools for proving Poincaré inequalities. I would like to focus on one of them among many, which is what is often called a particular case of the Bakri-Henry theorem, but is actually a bit older, is that if we look at uniformly convex potentials, so if the Hessian of the potential V is bounded from below time by alpha times the identity with some positive constant alpha, then we can control the Poincaré constant by 1 over alpha. So of course, the larger alpha is, the smaller the Poincaré constant is, and the better the inequality becomes. So to my knowledge, the first time this result appeared explicitly is in a work by Braskamp and Lieb in the late 70s. But in our modern understanding of this kind of inequalities is that essentially this is a particular case of the modern generalization of a result of Lichner-Rovitz in the 50s. And then there were later works by Bakri-Henry, and a later work by Caffarelli reproved this result using optimal transport. So this is actually a sharp bound in general, because it actually captures the best constant for Gaussian distribution. If you look at the standard Gaussian distribution, so V is like 1/2 of x squared up to a constant, then the sharp constant there would be 1. And indeed, it turns out that the constant 1 is the sharp constant for the Gaussian distribution. So in general, this is a sharp result. And also notice that the dimension plays no role here. So it's completely dimension free, and this is crucial for many applications. Okay, this result is actually the kind of the Euclidean version of a more general statement that actually says that in the geometric setting, what matters is a lower bound on the Ricci curvature of the manifold. This is actually the content of Lishnerowitz's theorem. And which is why we often talk about these lower bounds on the Hessian as a curvature lower bound, because it really plays the same role as the curvature in the geometric setting. Okay, so there are, as I mentioned, there are many proofs of this. One way is via the Bakri-Emery gradient estimate, which states that if PT is the semi-group generated by the generator L, so it's PT is exponential of minus TL here. Then the gradient of some PT applied to some test function F is exponentially decaying with a prefactor that's PT applied to the norm of the gradient of F. So we have a subcommutation relationship between the semi-group and the norm of the gradient with a prefactor that's exponentially decaying. That's like exponential minus alpha t, where alpha is this lower bound on the Hessian. I will not prove this because I will later give a sketch of a proof of a more general statement. But given this subcommutation bound, the proof of the Poincaré inequality is quite easy. So we can rewrite the variance of F as the integral of the derivative of the L2 norm along the flow generated by the semi-group. But a computation shows that the derivative of the L2 norm along the flow is the L2 norm of the gradient. So the variance is really the integral of 0 to infinity of the integral of the L2 norm of gradient PTF, average from time going from 0 to infinity. And then if we plug in this this gradient bound, I forgot a factor 2 here. This is less than exponential of minus 2 alpha t times pt of grad f squared. But now if we average pt of grad f against mu, the pt doesn't appear anymore because mu is invariant under the flow. So now we can reintegrate the exponential, and we get that the variance is bounded by the L2 norm of the gradient with a prefactor 1 over alpha. And more generally, if we want to prove a Poincaré inequality, it is enough to get a gradient bound, an exponentially decaying gradient bound for Lipschitz test functions, and we can afford for a prefactor actually. Okay, this is because of the spectral nature of the inequality. The prefactor doesn't really matter in the end.
So Max, sorry to interrupt, but it's enough to show it just for one Lipschitz functions? Are you assuming like convexity?
Okay, here I'm assuming when Lipschitz functions are nicely dense for a core.
Okay, but you would just get a good bound on the variance for one Lipschitz functions, no?
So if sorry, not one Lipschitz. No, if you okay, what you're saying is right that the variance bound is not enough unless we assume convexity. Yes, you're entirely right. And this is my bad for recycling slides from half a year ago.
But if you put the Lipschitz norm on the right hand side, it's fine. So
yeah, you're right. There's a you need to take into account the Lipschitz norm. Yeah, because then if you run the spectral expansion, you see that what matters is really the rate of decay and not the prefactors. But this is assuming that Lipschitz functions are nicely dense. And of course, it's not one Lipschitz function, it's Lipschitz functions. Okay. So another consequence of these gradient bounds is the convergence to equilibrium in W1 distance. So what's the W1 distance? If you look at two measures mu and u, so this L1 Wasserstein distance is the supremum of the difference of averages over all one Lipschitz test functions. And by convex duality, this is also the minimization in an optimal transport problem, in that if we look at all couplings of mu and u, so here this is the infimum over all measures pi on the product space whose first marginal is mu and second marginal is nu. And then we minimize the L1 distance over all possible couplings. These two quantities coincide and they define a distance on the space of probability measures, which metrizes a weak convergence plus convergence of the first moment. So it's a nice distance on the space of probability measures. And if we have a gradient bound, then it also implies convergence to equilibrium in Wasserstein distance, because one Lipschitz functions become more and more Lipschitz. So if we have this gradient bound and we apply it to a one Lipschitz function, we see that Pt of f becomes exponential of minus alpha t Lipschitz at positive times t. And then the Wasserstein distance between the law at time t and the equilibrium measure, we can write it as the supremum over images of Lipschitz functions by the semigroup Pt. And because they become more Lipschitz, we get an extra prefactor that's exponential of minus alpha t. So this gradient, this is not in general equivalent to Poincaré inequality itself. This is just to say that gradient bounds imply convergence to equilibrium for two different notions of metrics. And often this Wasserstein 1 distance is a better metric than L2 convergence for high dimensional applications. Mostly because for kind of generic data, this prefactor here scales like square root of the dimension, because this is like the size of the typical distance between two measures, while the prefactor in L2 convergence here is typically exponential in the dimension. Okay, so the motivation of what I would like to talk about today is about weakening the requirement of a uniform lower bound on the Hessian V. And the starting point is a general representation of the gradient of Pt of f. So if now we look at the Hessian of V at some point x, and we look at the lower bound on the eigenvalues, so I'm assuming that at a point x, the Hessian of V is controlled by alpha of x times the identity in the sense of symmetric matrices for some function alpha. And in what follows, what matters is that alpha is bounded from below, but not necessarily by a positive constant. It can be any constant. We kind of need it to be bounded from below to assume that everything is nicely well posed. And then we can show that the norm of the gradient of Pt of f evaluated at some point x is bounded from above by the expectation of the norm of gradient of f evaluated at some point at the point xt. And this is the expectation for the diffusion process started at the point x, if I forgot to specify this, little x, but with some extra factor, which is exponential of minus the additive function of alpha along the trajectory up to time t. So in some sense, we are looking at how we accumulate curvature along a trajectory. And this is an extra exponential factor that bounds the gradient of Pt of f. And of course, if alpha is bounded from below by some positive constant, we immediately recover this Macri-Emery gradient bound. So I don't actually know where this inequality first appeared. So I first learned it in some work of Braun, Haberman, and Sturm, who proved this inequality in a much more broader setting of the so-called RCD spaces. So non-smooth metric measure spaces that are locally Hilbertian. But it has been known for a while, and this kind of formula actually goes back to work of Bismuth on Malevin calculus. So I don't know where this, yeah.
Could you comment on when is it sharp? This is so interesting.
So in the case where alpha is bounded from below by a constant, this is sharp. This is actually essentially sharp for the Oershteil-Uhlenbeck process. Actually, no. The L2 version of this is sharp for the Oershteil-Uhlenbeck process.
Right.
I'm not sure if the L1 version is sharp. No, actually, and there is one case where it is sharp.
But if alpha is not a constant, that's actually what I'm like. If alpha
so
is in
the
your
non-constant case sharpness is not, and no one has ever looked at sharpness.
You
as
have,
far as I know.
thought, but okay, yeah.
May I just comment? That
maybe, sorry, just to finish answering Galina's question, because there is one important case where the L1 version is sharp, is that if you look at the manifold with non-negative curvature, you have grad pt of f of x is less than exponential of grad f of xt, norm of grad ft. And actually, this is sharp if and only if the manifold splits off a line. So you kind of have an encoding of Chigger-Grummel style splitting theorems by these kind of gradient bounds.
Thanks.
Sorry,
Boaz, you had a question?
No, I just want to comment that there is an identity which is not so far from this inequality. So you can express the gradient of PTF as some kind of.
Yeah, this is the Bismuth formula in Malevin calculus. I guess that's where. So yeah, so Bismuth has some work on exact representations of gradients and Hessians of PTF. And if you start looking at this formula, you can deduce from them these kind of bounds. So now I would like to give a sketch of the proof here. No, not of the general Bismuth formula, but just of these bounds. So what you can do is that you can couple two processes with starting from different initial conditions, but using the same Brownian motion here. So this gives you two realizations of two stochastic processes, but they are coupled. And using the lower bound, that's a lower bound on the gradients by well, the scalar product between gradient v, difference of gradients of v, and 2 points by the kind of the curvature low bound average on the curve going from the 2 points. We can show that in a pointwise sense, this quantity is monotone, just from the coupling. So you differentiate this in time. You write down the Ito's formula, and you can get that this is decaying. This is decaying. So in particular, it's bounded from above by the initial condition, which is just the distance between your initial data. And now to go from this to the gradient bound, you can test out expectation of f of xt with some Lipschitz function, divide by x minus y, let y go to x, and then this as soon as you assume at least alpha is continuous, this you end up with alpha of this quantity here. So you indeed end up with the additive functional of your curvature lower bound along the flow. Okay, so now if we only consider one Lipschitz functions, this here, the dependence on the endpoint, we can simply bound it by 1. So we can get that gradient of PTF of x is bounded from above by the expectation starting from x of the exponential of your additive functional of alpha. And so to prove either convergence to equilibrium in W1 distance or some kind of Poincaré inequality, what we aim is to get a bound of the form the expectation starting from some point x of this additive functional, we aim to get some kind of exponentially decaying bound with possibly some prefactor. The prefactors don't really matter. But of course, because of the ergodic theorem for Markov process, we expect that the additive functional along the flow scales like t times the expectation at equilibrium. So what we kind of expect is that this should kind of decay like exponential of minus t times the average of alpha and not its lower bound. At a first glance, this is what you might expect. And why would this replacement of the lower bound by the average is interesting? We had two main motivations. One is, of course, as you can guess, is that if the curvature is negative in some small region, but positive in most spaces, we don't have a uniform positive bound, but the average curvature should still be nice. So and in these situations, we actually do expect that exponential convergence to equilibrium to still occur. So maybe average curvature would be a good tool to kind of quantify this. And the second motivation is that even in the case where alpha is bounded from below by a positive constant, the Bach-Riemann theorem is actually sharp in the sense that rigid in the sense that we have equality here if and only if we have equality here pointwise almost everywhere. So the only measures for which the Poincaré constant is exactly alpha minus 1 here are measures for which, in a pointwise sense, the smallest eigenvalue of the Hessian of V is also alpha. And actually, these measures are product measures where one factor is Gaussian. So we kind of have a splitting theorem in that we have equality in the Bach-Riemann theorem if and only if the measure splits off a Gaussian factor. This is a particular instance of geometric theorems that were proved by Cheng and Zhu and Jili, Ketterer, Kueda, and Ota a few years ago. And so what happens is that any positive variable truly variable curvature bound should lead to a strict improvement of the Bach-Riemann bound. In that any case where we have this bound by some positive constant, but where this function alpha of x is not constant, the Poincaré constant should be strictly better than the one predicted by the constant curvature case. And a result in this direction was already obtained by Vesser in 2011, where we showed that we can replace the pointwise lower bound on the curvature by a harmonic mean. So the 1 over the average of 1 over alpha, as soon as alpha is strictly positive everywhere. So what I will talk about a variant of Vesser's result, but that is not directly comparable. Okay, so that's the nice picture, but the picture I just described cannot work. We actually cannot expect this exponential decay to hold with a prefactor just the average of the curvature. And it already should break down in dimension 1. And why is that? Well, what's the best possible lower bound on the eigenvalues of the Hessian of V in dimension 1? Well, it's just the second derivative of V. So the average curvature is going to be the average of the second derivative of V with respect to each exponential of minus V. But we can integrate by parts, and this is the average of V prime squared. So it's always strictly positive. So we always have strictly positive average curvature in dimension 1, but we don't always have exponential convergence to equilibrium. It is not too difficult to produce examples of V's that do not grow to infinity fast enough for such exponential decay to occur. For example, if you take V of x as some kind of constant times log, we get some kind of polynomial decays to equilibrium, but we don't get exponential decays to equilibrium. So the picture that, well, maybe we can just replace uniform lower bounds by average of curvature is too optimistic. It's not going to work. And what is the gap? The gap is that the ergodic theorem is qualitative. This is the limit. But what we would need here is to do some kind of quantitative ergodic theorem to get such a bound at a fixed time t. And it is in so what we need is a rate of convergence. Maybe not for everything, but at least for the observable alpha. So and the principle here is that if we have some quantitative ergodic theorem for a single observable, then we can deduce rates of convergence to equilibrium for in L2 for Wasserstein distances and for other norms too. Okay, so how do we get bounds on the ergodic rates of convergence in the ergodic theorem? One answer was given by a theorem of Guillen, Leonard, Wu, and Yao about 10 years ago, which is the following. It shows that an equivalence between bounds on probabilities of seeing a significant deviation in the ergodic theorem and certain types of functional inequalities, which are known as transport information inequalities. So the statement is that for any one Lipschitz function with respect to some distance d, which is not necessarily the Euclidean distance, having some kind of exponential upper bounds on probability of deviation, starting from some initial data that has a density with respect to mu, and then with a prefactor that's like the L2 norm of the density, is the same as being able to bound the Wasserstein 1 distance, but with respect to this particular distance squared by the Fisher information. So the L2 norm of the gradient of the log of the density. So we have a reference measure mu. We look at some other measure with the density rho, and always being able to bound Wasserstein 1 distance by the Fisher information is equivalent to having exponential bounds on the probability of observing significant deviations. And the insight behind this theorem is that the Fisher information is actually the large deviation rate function for large deviation principles for additive functionals. Okay, so this theorem gives a kind of a functional tool for controlling errors in the ergodic theorem, at least for observables that satisfy a regularity estimate. And then by Markov's inequality, from this we can really get actual rates of convergence in the ergodic theorem. And there are two subcases of interest here. One is the case where the d is the Euclidean distance. So now we get the standard Wasserstein distance. And this functional inequality is something that is known. It kind of has a place in the hierarchy of functional inequalities. For those of you who know it, it's weaker than the logarithmic Sobolev inequality, but it's stronger than Gaussian concentration for mu. So for it to be true, we at least need V to grow quadratically at infinity. But there is another interesting case, which is when D is just a discrete distance, so indicator of 2 points differing. And then the admissible test functions are just bounded functions. So Lipschitz functions for the trivial distance are just bounded functions. And the functional inequality, this transport information inequality, is something that is actually strictly weaker than the Poincaré inequality itself. And indeed, we can show that if a Poincaré inequality holds, then this inequality holds with D, the discrete distance, and the constant here that is 4 times the Poincaré constant. So these are two examples that come to mind, but of course, in principle, we could work with different distances too. So one application now of this kind of combining these rates of convergence in the ergodic theorem and the variable bound on the variable gradient bound is a kind of a self-improvement in the Bakry-Emery bound. So say the Hessian is bounded from below by some function of alpha, which is itself bounded from below by some positive constant. Then we can bound the Poincaré constant from above not by 1 over alpha 0, but something strictly smaller with a gain t that looks at the difference between the average of the curvature and the curvature lower bound, and adds in something extra that depends on the oscillations of alpha. So you can think of this as being the sup of alpha minus the inf of alpha, and some extra factor here that also depends on how far the average of the curvature and the uniform lower bound are. And this is always a strict improvement for measures that have full support and for which the average curvature is strictly better than the uniform lower bound. So it's a strict improvement for any measure that has full support and does not have a Gaussian factor. So that is not a product measure with one factor being purely Gaussian. So, okay, so this kind of quantifies the idea that Gaussians are the only cases in which the Bakry-Emery bound is sharp. So maybe to give you a brief sketch of the proof. So a priori, we know that the Poincaré constant is bounded from above by 1 over alpha 0. And we know that this implies this transport information inequality with a constant that's 4 over alpha 0. So we have a rate in the ergodic theorem, and we plug it in here. So we take our curvature functions, we deduce a bound on this quantity from the a priori bound on the Poincaré constant. Okay, so first in the probabilities of deviation, and then on the expectation, on the expectation starting from a point. And from this, we deduce we take the gradient estimates, and we deduce an a posteriori bound on the Poincaré constant from this kind of argument from this gradient bound that is a posteriori strictly better than the one we started with. So we kind of have an automatic self-improvement of the Bakry-Emery theorem as soon as the average curvature beats the lower bound. So, okay, so that's just one example of implementation of this strategy. I will not discuss other ones because it quickly becomes very zoological. We have other ways of implementing this. We can use log Sobolev inequalities. We can replace the average of the curvature bound by some kind of median. We can use other kind of concentration inequalities. And this is kind of like, okay, kind of a whatever works strategy. What matters is that you have plenty of ways of getting rates of convergence in the ergodic theorem. And what matters here is that actually we only care about a single observable. So you can also try to get an estimate on this hands-on on one particular example using, say, couplings or Gershenov type estimates, or a lot of tools are available. Lyapunov functionals approach, and then deduce some kind of rate of convergence in the ergodic theorem, and then plug this in the strategy I just described to then deduce rates of convergence to equilibrium. Just a few other notes. This can also be used to get convergence to equilibrium in Wasserstein distance of order p. So by which I mean you take this definition, but you add in a power p here in the infimum overall couplings. So these become stronger distances on the space of probability measures. And because what's really at the core of the argument is a kind of a coupling argument, you can also get bounds on rates of convergence in Wasserstein p distance. The rates become worse as p grow large. And we also need an extra technical requirement in that we need to strengthen the Hessian lower bound into some kind of pointwise lower bound that only depends on the endpoints. So the scalar product between grad v of x and grad v of y, dot product x minus y, should be bounded from below by x minus y squared times a prefactor that only depends on the endpoint. So it's kind of stronger than the requirement here that we had used in some kind of interpolated way. The point here is that we kind of need to make it depend on to get Wasserstein distance estimates. We can only care about the endpoints and not about what happens on the path to interpolate between the 2 points. Okay, so for example, this can be used to get WP rates with P strictly larger than 2 if a log sub F inequality holds. That's for one example among many that you can get out of this. Okay, so that's about all I wanted to discuss today. Thank you very much for your attention.
Thank you, Max, for this very interesting talk. Are there any questions to Max? So may I ask a question? It could be that you already answered during these 15 seconds that I could not hear you. So what's the, you just mentioned in passing this result by Visser about Visser.
Yeah.
Can you elaborate?
So what you can show is, what he showed is that you can bound the Poincaré constant by the harmonic mean of this function alpha of x. So assuming it is strictly positive, you average 1 over alpha. Then you take the inverse of this. So this is strictly better than the lower bound, but worse than the average of alpha. And from this, you can get also get a bound on the Poincaré constant. So the two results are, this result is not comparable with what I described in general, because in the implementation of this strategy, we never get as a rate the true average, but we also get always get some extra terms that depend on the rate of convergence in the ergodic theorem. So we never get the true average, but always something a bit worse.
I see. And is there any hope for a matrix version of alpha, or this is beyond any? Okay.
Maybe this is. I mean, yeah. So, some natural question is to try to get some kind of Braskamp-Leib version of this result. Good question. It's a bit harder to get kind of hands-on controls on the matrix version by this kind of coupling arguments. So first thing one would have to do is some kind of dispute formula with matrix weights.
This exists.
Oh, okay. Okay, so this actually exists already? I don't know.
I think. Okay.
Max, can I ask a question?
Yeah.
Max, can I ask a question?
Yes.
I must be missing some technical point in your proof, but it looks to me that you need to control a lower deviation, large deviation for the integral of alpha xs being small. So you really need to worry about r being negative. And in that case, I don't see why the kind of Gaussian bounds you get from the information transportation.
So here, the version I kind of described where everything works nicely is we have a uniform positive bound, and then we bootstrap something stronger. If alpha is allowed to be negative, well, you kind of have an optimization problem that comes out of it, in that you have some loss from the negative parts, you have some gain from the parts where alpha is positive, you have some loss from the rate of convergence to the ergodic average, and you have to figure out if everything balances well to get an estimate. So what really matters.
But what I'm missing is this: if CI would have been extremely large, then I think you will lose.
If CI is extremely large, and yeah, it is possible in some regime where the fluctuations of alpha are large and CI is really large, that in the optimization we just don't get anything.
Okay.
This is possible.
So it's important here that CI is related to CP. That's crucial to being always successful.
So the fact that it's always successful in the application to the self-improvement in the Back-Lemery theorem is indeed because CI and CP are already a priori related.
Okay.
If we have kind of no connect, so maybe to give you an example where everything is going to break down. no, okay, no, sorry. The example I was thinking of is not going to work. But yeah, okay, yeah, one example where everything is going to break down. Imagine a situation where alpha is positive on a very large region, but negative at infinity. Then, okay, this is not going to work, really. Well, if you try to work with this CI, it's not going to work because CI is going to be infinity. But yeah, okay, you can build by hand examples where you have some CI that's terrible. The oscillations of alpha are large enough that CI is not good enough to compensate, and you try to optimize and you get something that's never good.
Thank you.
Question, Max. I'm sure you thought of it. So in this, is there a version of this theorem where you replace the usual Wasserstein by mass, Jan mass, or Erber mass curvature?
So one thing that's going to be, we haven't tried to implement this because what's the really annoying thing in the Erber mass setting is that to define the curvature, we need to lift everything to the space of probability measures. So the analog of some variable curvature bound is not going to be something that's going to live on the physical space. It has to be a function of probability measures. And now we get up at some non-trivial ways. Well, maybe there is a way of connecting everything, but it's not going to be as nice as this because we are really to define the variable curvature, we really have to lift everything. So what's the natural way of lifting the ergodic theorem to connect things? And then the other thing that's not so nice is the fact that in the discrete setting, the Fisher information used for the transport information inequalities and the natural Fisher information in the gradient flow structure, so the entropy productions, are not the same anymore.
Right.
So that these are kind of the two sources of why it would certainly be a non-trivial endeavor.
Yeah. Thank you.
Any further questions to Max?
Yeah, can I ask a question?
Sure.
Oh, hi, Max. Thanks for the talk. Is there anything interesting to say about cases of negative curvature?
So as I said, it's like you can show examples where you have negative curvature in some region, positive but positive at infinity, and show by hand that you can get estimates out of this. I didn't show any example because it's all we did is extremely zoological, really. It's like, give me an example, we try to do things, and if things are not too bad, we can do it. But it's like we don't have a nice meta theorem in the same way as this. It really is. Here's an example. Here's how to try to tackle it, and maybe it works, maybe it doesn't. So yes and no, I guess.
I see. Thanks.
Maybe just to continue on Dan Mikulinsel's question, I think, suppose you consider the other extremes that you have, say, a surface of genus 2 with hyperbolic metric, constant curvature -1. Is there anything? Well, maybe it's
no. I think if you do this, we do have expansion of distances along the.
Yes.
I mean,
so
we have an expanding coupling of the two.
Right. So nothing. Okay, any further questions? So let's thank Max again, and we meet again at 11:30 Pacific time for Galina's talk. Bye-bye.